20.3, motional EMF. In section 20.2, previous section, we considered EMF induced in a circuit when the magnetic field changes with time. It could be the strength of it, the P itself change, the cross-section, the A, or also the angle, the orientation of the loop considered within the B, the external B considered. Motional EMF, it means that the EMF induced or produced whenever there is a motion, okay, of a conducting bar. For example, you have a long straight conducting bar like this, placed within B external of into the page, alright, and this conducting bar is pulled to the right at constant velocity. Okay, whenever it is pulled to the right with at the constant velocity here, okay, a free charge, the free charge within this conductor, okay, going to experience F magnetic, okay, based on right hand rule number 1. So place your index finger along V direction, your 4 fingers along B, which is into the page. By default, okay, by right, your thumb is pointing upward. Your thumb is pointing upward. So by default, for positive charge, is going to experience F magnet upward like this. However, okay, positive charge cannot simply be moved within an atom because it is bound to the nucleus of an atom. So the one that freely can be moved is actually electron. So consequence of the motion and being placed within this B external, the electron now going to move downward direction, because upward by default for positive charge. Remember, for negative charge is going to be opposite direction. So it's going to be moved to the bottom part of the conductor. Alright, where it's going to leave, okay, the pair of it, the positive charge on the top of the conductor. So this separation going to cause an electric field, okay, established between these two ends. Alright, so firstly, okay, we know that the F exists or experienced by the electron is QVB sin theta. Alright, what is the theta? Between the angle between the velocity and the magnetic field. Right. So if you refer to this drawing or diagram, the B and the velocity is perpendicular to each other. So the V and the B is perpendicular to each other. Therefore, sin theta becomes sin 90, which give you 1. Right. So, okay, F magnet experienced by the electron will be simplified to this only. Alright. So since on the top here, okay, will be positive charge accumulated, and then on the bottom here will be negative charge accumulated, and electric field, okay, in this direction going to be established within this conductor. The F coming from the E experienced by the electron will be QE. F due to the electric equivalent to QE. Alright. And then which direction to be? Okay, the direction going to be for electron going to be in opposite direction to the E. Okay, for the electron is going to be opposite to the direction of the E. So the electron going to experience a force upward. This is of electric, due to the electric. Therefore, okay, the separation process between proton and electron going to be stopped whenever the Fe here, okay, is balanced with this F magnet. Right. So what does that mean by balance? So means that, okay, F along E must equals to F according to or due to the magnet. So this is QE and this one is QVP. So the Q cancel out. Therefore, we have this kind of E equivalent to VB. And not to forget, E equivalent to VB. Not to forget, from previous topic, we've learned that delta V or EMF, potential difference within an established electric field, is equivalent to EX, or in this case, EL, because this is the separation distance between the top section and bottom section. So, okay, well, we will have, okay, another term of this. So delta V is equivalent to EL, okay, equivalent to the E itself is VBL. Normally, we're going to put it in terms of BLV. Right. So what is the unit of the delta V here? It must be in volt. Okay. Provided that the rest of the things also in SI unit, where the B must be in Tesla, the L must be in meter, the velocity must be in meter per second. Alright. So, okay, the EMF here, okay, the EMF here also can be used in terms of symbol of this. Alright, is equivalent to BLV, was produced due to the motion of this conducting bar within an external B into the page for this situation. So this situation will be more interesting, okay, if now you have this conducting bar is placed within a complete circuit like this. Right. So now in this situation we have a fixed railing bar. Okay, two railing bar here are fixed, okay, connected to one load of resistor, okay, and then the moving conducting bar placed on the top on the railing bar, okay, and pulled to the right. Right. So pulling this will cause, okay, the loop here, the area of the loop here, this is constructing a loop of conductor. Okay, so the area covered by this loop of conductor will be increasing, isn't it? So whenever area is increasing, flux going to change. As we recall, flux is equivalent to BA cos theta. Right. So the theta is actually angle, the smallest angle between the B and the normal line of the A. So for this situation, okay, let's consider the area, the normal line of the area is into the page. The B as well is into the page. So it's gonna be cos 0. Cos 0 will give you 1. Alright, so we are left with BA only. Alright, so increasing of A, the A is increased because when the bar is pulled to the right direction, the A will be increased. so the flux also going to increase, right? So it means that the flux now going to experience changes due to the changes of A. So whenever you have a change of flux, okay, with time, you're going to have the induced EMF, induced B, induced current going to be produced, right? So check what kind of changes just now. The changes just now, increment of A, increment of flux. So increment of A going to cause, okay, another B induced, okay, which is opposite to the B original, where the B original now is into the page. So the B induced going to be out of the page. So this is your B induced, right? Okay, by using Grepp's rule, you may now determine the direction of the current induced produced within the loop here. So our focus is at the center here. B induced going to be out of the page. So the B at the center of the loop is out of the page. Grab your conducting bar here. Your thumb is pointing upward like this. This is your I induced, where it's going to establish within this closed circuit, right? So this is your I induced. Right. So, okay. What does that mean by this one? FM here. Okay. Whenever the current already established, okay, moving, flowing within this closed loop, okay, then it is placed within magnetic field. Then it brings us to another formula, which is BIL sin theta. Still remember? Okay. So the direction here, Madam going to explain in detail later on. But as of now, we are taking into consideration about the EMF produced. Okay. So the EMF produced within this closed circuit, okay, produce B induced, which is out of the page, and I induced going to be counterclockwise direction like this. So this drawing or this situation, physical, this is physical situation, can be transferred or converted into circuit diagram like this. The EMF here, again, we are going to take a look later, just a moment after this, is equivalent to BLV. So how to get this, right? This one. So just now, the bar being pulled to the right, isn't it? By F applied. The bar is being pulled to the right by F applied. Alright? So the area going to be increased. Okay, the area going to be increased by this portion. Alright? Due to the displacement to the right by delta X of the bar. At any instant, the bar that immersed within the field is L of length. Okay, and we know that based on Faraday's law, EMF is directly proportional to the rate of change of flux. Okay, so the one that changing right now is the area, right? So the area, okay, is L times delta X. Because area in this situation is L times delta X. So the flux, change in flux, is actually caused by change in area, which is B L delta X, the area. If you're talking about rate of change of flux, okay, over time, then this one will be over time. So this one over time will be the velocity. So that is how they figure out the formula for this situation. Okay, and then this is about Ohm's law. Okay, I equivalent to, okay, this is actually coming from I equivalent to delta V over R. Okay, so your delta V right now is the BLV. Alright then. Okay, let's try question number 30 from your textbook. So we know that delta V equivalent to BLV, right? And then our interest based on Ohm's law, I equivalent to delta V over R, and your delta V here is BLV over R. Okay, we need to know the V. V is equivalent to IR. Rearrange the equation over BL, right? Then you will get, okay, substitute the value 1 times 6 ohm over 2.5 times 1.2 meter. So you will get the V is 2 meter per second. Right, that is for part A. For part B, okay, what power is delivered to the resistor? So for part B, we are going to calculate power. Power equivalent to, it's requested for I square R. That is the information that we can gather. So I square R, 6 ohm. So you have 6 watt of power. How about C? C, what the magnetic force is exerted on the moving bar. So C, magnetic force, F. So F here, this is the one, BIL, okay, sin theta, right? The angle between the length and the B is 90 degree. So it's become 1. Sin 90 is 1. And then you have here F equivalent to 2.5. The current is 1. And then the length is 1.2. Right? Where it's going to give you 3 Newton as the answer for the magnetic force. The D, what instantaneous power is delivered by the force F applied on the moving bar? Okay, so bear in mind that this moving bar is moved, okay, at constant speed. When you have a constant speed, means that the A will be 0. There is no acceleration. So for part D, alright, F applied to the right, okay, minus, okay, F magnetic to the left. F magnetic will be opposite. Okay, why is it my opposite? Because BIL, your, okay, your I, okay, remember the change? What kind of the change? The change is increment of the loop here, area here. So it's going to produce B induced, which is in opposite direction. Okay, so the B induced in this direction. By using Grab's rule, I induced will be in this direction. Okay, established in this direction. That is how we know that the FM going to be in this direction based on this law. Place your B, okay, current, Your index finger is your current. Your B external is into the page. And then your thumb is pointing to the left. That is how we know the direction of this F based on this, yeah. Alright. So then now back to the calculation of the D, part D power. So we need to figure out the F net firstly. So F net, F applied minus F magnet, right, is equivalent to 0. So F applied equivalent to F magnet, alright, where, okay, power due to the F applied is equivalent to F applied times with the velocity Fv, yeah. So F applied equivalent to Fm. Here is the Fm, right, which is 3 times the velocity just now, 2, which give you 6 watt again. Alright. So either way, whether you calculate it by using this or you calculate by using the method, you will get the same answer. Okay. So that's it for question number 30 as your example. So now we're going to take a look in detail. Madam going to repeat again on the direction, on how to determine the direction. Okay. So let's say we're going to consider again the same situation in detail right now. Alright. So we have this conducting bar is moved to the right at constant speed. Okay. B external is into the page. Alright. By using right hand rule number 1, okay, we know that positive charge will be accumulated at the top. Negative charge will be accumulated at the bottom. So the current going to flow into this direction within this conductor. So if this is the direction of I induced based on BIL sin theta, F magnet equivalent to BIL sin theta. Okay, your L, right? So it's perpendicular to each other. Therefore, you will have sin 90 equivalent to 1. Right. So the direction of the FM here, place your index finger along the I, right, which is to the top of the conductor, and then your forefinger, the rest of the 4 fingers is into the page. Your thumb is pointing to the left, right? That is how we know this direction, right? We want to check in terms of flux. Okay, the area again increase. Okay, that is why in simple the F magnet going to pull the bar to the left so that the area will be decreased in amount. Remember, all kind of the induction things don't want to change. That is a keyword. So it want to maintain whatever previous situation. So you don't want to increase of area of the loop. Alright. Next one, if let's say the bar now is pulled to the left, what will happen? Okay, in simple, the area of this loop going to be decreased. The flux also going to be decreased. So all the induced things don't want to have the change. So the decrement just now is the change. So the F magnet going to be in opposite direction, okay, pulling the bar to the right, okay, because it don't want to experience the decrement of area. The decrement of the area will cause the decrement in flux as well, because, okay, flux is equivalent to BA cos theta. Cos theta here, okay, the normal line between the A normal line of the A to the B. Okay, it could be 0 or 180 degree. Whether this one become 1 or negative 1. Doesn't matter. Right? So this one, let's say, become 1. So, okay, the flux, okay, going to change whenever the A is changing. Right? Changes of the flux per unit time will cause, okay, EMF produced, which is P change in A over time taken. Right? So we have to check what kind of changes happen. So the changes happen just now. The A is decreasing. So the flux going to be decreasing. Okay, that is why the F magnet is to the right, so that the area will be maintained. Because the induction, the induced things don't want to change. That is the keyword. Right?